Okay, so what we're going to look at in this video is a way of introducing integration to more able students. I've called it integration from first principles because it's very similar in flavour to differentiation from first principles. What we're going to do is we're going to look at how we might derive or justify the formula for integration. Okay, so what we're going to need to recall is the formula that we've used for differentiation from first principles. So just to recall that the derivative of a function at a point is equal to the limit as h tends to 0 of f of x plus h minus f of x all over h. So you probably know that integration and differentiation are linked. There's a famous theorem that links the two. So what we're going to do is we're going to look at how we might derive such an equation. We are going to make some assumptions along the way, some simplifying assumptions. The idea behind the derivation is absolutely correct, even if the derivation might not be as rigorous as you might find in a book on analysis, maybe something like that. But it will certainly be good enough for our purposes. Okay, so the aim of integration, at least initially, is to figure out areas. Areas under curves in this instance. So we can see from this picture here, I've just sketched a very quick curve and I've shaded in purple the area between the 2 points A and B on the x-axis. And this area we're going to denote with the usual notation. So it's the integral from A to B of f of x dx. So those set of symbols, we're not going to attach too much meaning to each of those symbols individually. So the dx, what exactly is the dx? Well, that's not quite such an easy question to answer. So what we're going to do is we're just going to say it comes with the integral symbol. So those set of symbols all together, the integral from a to b of f of x dx, they all refer to collectively the area under the graph of y equals f of x between a and b on the x-axis. Okay. I've drawn it as line above the x-axis here. That's going to be one of our simplifying assumptions. Obviously, we all know that when the curve dips below the x-axis, then we have to subtract the required amount of area. Okay, so how are we going to figure out what this area is? Well, the key idea is to define this new function, big F of x. Now, big F of x is going to be defined to be equal to, so whenever I use a colon and an equal sign, as I have done here, that means I'm defining the thing on the left to be the thing on the right. So if you haven't come across that before, that's what that means. And I've written it in words here, just for ease. So big F of x is going to be the area beneath the graph from 0 up to x. So again, we've got another little assumption coming in here that the area that we're interested in question lies to the right of 0. That just makes our pictures a little bit easier to draw and visualize. There isn't really any real reason for that, and certainly the result is true, obviously, regardless of where you are on the axes. But again, for the purposes of the picture, we're just going to define f of x to be the area beneath the graph from 0 to x. We'll actually see that the 0 is completely irrelevant. So if we go back and look at the picture that we just had, we can see that if we want to figure out that purple area, then one way of doing this is to take the area from the origin up to B, so the area from the y-axis, if you like, all the way up to B, and then subtract off the area up to the point A, because that would then leave us with the purple area. So it could be the area under the graph from 0 to B, subtract the area under the graph from 0 to A. Okay, so if you need to pause and have a think about that. So in other words, we go back to this key idea, we have our formula. We have that the integral between a and b of f of x dx is equal to big F of b, which is the area beneath the graph from 0 to b, minus big F of a, which is the area beneath the graph from 0 to a. But of course, we haven't really solved the problem, we've just rephrased it. Because we don't know what big f of x is. If we had some way of figuring out big f of x, then we'd be done. But we don't. So let's see if we can figure out what big f of x is. Okay, so in this next picture here, what I've got is I've got the same curve, but I've drawn a little purple strip here. The strip really, you might want to think of as being a little bit thinner, possibly, but I've drawn it nice and thick here, just so that we can easily see what's going on. So the area of the purple strip is the area under the graph from 0 to x plus h minus the area under the graph from 0 to x. Okay, just as before with the a's and b's, now we've got the area under the graph from 0 to x plus h minus the area under the graph from 0 to x. And you can see I've written that there in purple. Okay, so on this second picture with the green rectangle, what I've done is I've done exactly that. I've drawn in this green rectangle. Now the first thing to notice is that the area of the green rectangle that I've now shaded in is less than the area of the purple strip. Okay, so if you go back and have a look at the purple strip, then have a look at the green rectangle, what you'll see is that the area of the green rectangle is less than the area of the purple strip. You can see it on that picture. And obviously, again, the way that I've drawn the curve makes this so, and could I possibly draw the curve in such a way that it wouldn't be so obvious? Yes, but again, we're just assuming we've got these nice, smooth curves that we can draw nice and easily, so that we don't have to get too technical with our definition of the integral. So what is the area of this green rectangle? Well, what's the width? The base goes from x to x plus h. So clearly, again, on my drawing, h is a small positive number. H could be negative, but again, just for the purposes of this illustration, we're taking h to be positive here. So the area of the green rectangle is the width of the rectangle, which is h, little h, times the height of the rectangle. Now, what's the height of that green rectangle? Well, remember that the curve is y equals f of x, and the top of that green rectangle is precisely the point on the curve where the x value is little x. So I'm sort of overloading what little x means here, but this is not uncommon. We use it all the time for derivatives. So the height of that rectangle is little f of x, and you can see I've actually drawn a green dotted line across just to kind of illustrate that. The curve is y equals f of x, so certainly the height of that little green rectangle is f of x. So the area of the rectangle is the width times the height, which is going to be h times f of x. So you can see I've written that up the top there. The area of that green rectangle is h times f of x. And the important thing to notice is that it is less than the area of the purple strip. Okay, so in this next picture, what I've now got is I've now drawn a blue rectangle. The first thing to notice is that you can see that the area of this blue rectangle is bigger than the area of the purple strip. Okay, you can see that the area of the blue rectangle actually includes area above the curve. Okay, so you can see it includes everything in the purple strip, which you can still see with those purple lines. And in addition to that, the area above the curve. Okay, so the area of the blue rectangle is bigger than the area of the purple strip. What is the area of that blue rectangle? Well, again, exactly as before, we can see now that the base is h, as before, little h. But the height of the rectangle is now, well, you can see its height is the y-axis, the point on the y-axis, little f of x plus h. Okay, so if you look at that right hand side of the purple strip, that's at the point x plus h on the x-axis. Follow that up. Where it hits the curve is the height of the blue rectangle. As you can see, I've drawn the blue dotted line along to the left there. And what is the height? Well, it's y equals little f of x plus h, because that's the equation of the curve. So the height of the rectangle is little f of x plus h. So the area of that blue rectangle, which again is bigger than the purple strip, is h times little f of x plus h. So what have we got? If we put that all together, and I've highlighted the terms in green, purple and blue, just to make sure it's clear what we're doing here, we've basically got that the area of the green rectangle, which is h times f of x, is less than or equal to the area of the purple rectangle. The way I've drawn it was actually strict, but we'll keep the less than or equal to inequalities in here. It's not going to hurt anything. So the area of the green rectangle, which is h times f of x, is less or equal to the area of the purple strip. Now if you remember, the area of the purple strip was big F of x plus h minus big F of x. We don't actually have an expression for big F yet, that's what we're hunting for. But maybe we can do something clever here and we might be able to get some way towards an expression for it. So the area of that purple strip is then, once again, less than or equal to the area of the blue rectangle that I drew, which we saw had an area of h times f of x plus h. So if I take that top inequality there and I divide everything by h, again the way I've drawn it, h is some small positive number, so we can divide through this inequality and all the inequality signs stay the same. We're going to have f of x is less than or equal to big F of x plus h minus big F of x all over h, which is less than or equal to little f of x plus h. Now that term in the middle looks a little bit familiar. F of x plus h minus f of x all over h. It looks a bit like a derivative. So what we can do to each of the terms in this inequality is we can take the limit as h tends to 0. Now inequalities are actually preserved by limits. Strict inequalities would have to be changed to less or equal to inequalities, but the limiting process does not change any of these inequalities. The reasoning behind that is a little bit technical. Again, an introductory course on analysis is probably where you would find a rigorous proof of that. But we'll just take it as given for the time being. It's not a huge leap of faith to believe that. And you're welcome to look up proofs if you like. So okay, so taking the limit preserves inequalities. Well, what's the left-hand term? F of x. There is no h there. So that doesn't depend on h, that stays as it is. The term in the middle, well, it's the limit as h tends to 0 of big F of x plus h minus big F of x all over h. And hey presto, that is the derivative of big F of x. And on the right hand side we see that we have little f of x plus h. We're letting h tend to 0, so x plus h is going to get closer to x, so f of x plus h is going to get closer and closer to f of x. So in the limit, f of x plus h becomes f of x. Now we actually require, that's actually not true for arbitrary f, we require a property called continuity for that to hold. So again, I'm assuming that my function that I drew, the graph of the function, is nice and continuous, so that the limit as h tends to 0 of f of x plus h is equal to f of x. In fact, that is very often given as a definition for continuity. So what have we got? This final inequality, little f of x is less or equal to the derivative of big F of x, which is less or equal to little f of x. The only way that such an inequality can be true, because you'll notice that the two outside terms are the same, is if, on the next slide, the derivative of big F of x, so f prime of x, is equal to little f of x. Okay, that's the only way that the previous inequality could hold. So what do we know now about big F of x? Well, we know that its derivative is little f of x. So this is great, because that means that all we need to do to figure out the area that we was after is find a function, big F of x, whose derivative is little f of x. And this will be familiar, right? Because that's exactly what we've been doing when we've been working out these areas. areas under the curve, you take the function and then you find what's called an antiderivative, so a thing that gives you that once you differentiate it. These are sometimes just called integrals, but I prefer the term antiderivative. I think it's slightly more accurate as to what's going on. So our final result, i.e., is that the integral from a to b of f of x dx is equal to big F of b minus big F of a. Well, we already had that, but now we know that this is where the derivative of big F of x is equal to little f of x. So to evaluate this integral, all you have to do is find a function whose derivative is little f of x, plug in b, plug in a, subtract. The problem is this doesn't give us any information as to how to find an antiderivative of little f of x. It turns out that this is extraordinarily difficult and cannot be done in most cases. And in fact, the only places that it really can be done is in your A-level or calculus textbook. Okay, so I hope that was informative. If you need to, go back over the video, try and pick out the salient points, have a go at the derivation yourself, and I will see you in the next video. Thanks.